Alright, let's do, what do we got here? Differential equations. Whatever day this is, I don't even remember, but doesn't matter. Let's get on with it. Alright, so here I've got an interesting deal on Maclaurin. Maclaurin, when you do a series expansion for e to the x, or really any function for that matter, there becomes a nice easy substitution along with it. So e to the x is 1 plus x squared over 2 factorial, and down the line, as we know, x cubed over 3 factorial, and I'll stop there. Instead of taking derivatives of e to the x cubed and building your polynomial the way we've traditionally done, if it's a Maclaurin series, what you can do is you can just plug in x cubed everywhere you have an x. Oops. So I don't have a whole lot of space here, but what you'd have here would be x cubed to the second over 2 factorial, x cubed to the third over 3 factorial, etc. You'd just go ahead and simplify that, which would come down to, I don't know, 1 plus x cubed plus x to the 6th over 2 factorial plus x to the 9th over 3 factorial. I'm not going to simplify it for space purposes. Same thing here. So if you have e to the 5x, you'd still have 1 plus 5x plus 25x squared over 2 factorial plus 125x cubed over 3 factorial. And some of that can be reduced, that last term there, but I would, just for purposes of time and space, I'm going to leave it alone. Okay, so here's a really interesting one. X squared is already a polynomial, and I'm going to multiply it by e to the x. Therefore, that means I'm going to take x squared and multiply it by e to the x. So I'm just going to distribute this x squared to every term of e to the x, and I get a new polynomial. So I get x squared plus x cubed plus x to the 4th over 2 factorial plus x to the 5th over 3 factorial, and on and on and on. Some cool stuff there. So this is just the product of two polynomials. Let's try some more. Okay, so a Maclaurin more challenging substitution would be the following. I'm going to go ahead and write out the Maclaurin expansion out to, I think I'm going to go out to degree 3 on both of these, and you'll see why in just a minute. So give me a minute here. Alright, so I've got expansions out to the 3rd degree polynomial for both sine x and natural log of x plus 1. Those skills at this point should be skills that you've got in your back pocket, but I want to talk about the product of these two. So I'm just going to go ahead and I'm going to multiply both of the functions together to get a 4th degree polynomial. So I would get x squared, and then I would get, looks like negative x to the 4th over 6, and then I would get negative x cubed over 2, and then I would get x to the 4th plus x to the 4th over 3. Notice if I went out any further, or if I multiplied these two together, I'd get a term that would be larger than a 4th degree term. Therefore, I wouldn't do that. And therefore, it looks like I get x squared minus x cubed over 2 And the 2x to the fourth terms turn out to be a positive x to the fourth over 6. So there you have it. X squared minus x cubed over 2 plus x to the fourth over 6. Alright, so let's look at some tougher substitutions using a Taylor centered somewhere other than 0. So let's build e to the x centered at a equals 2. Third degree polynomial. Okay, so what I'd have here is f of a plus f prime of a instead of f of 0 plus f prime of 0 times x minus a instead of x minus 0. So I would have, of course, the derivative of e to the x everywhere is itself. So I'd have e to the a plus e to the a x minus a, right? So this would be e to the second plus e to the second x minus 2 plus e to the second x minus 2 squared over 2 factorial. I'm going to go out one more. So it'd be e cubed x minus 2 cubed over 3 factorial. Okay. In the second piece, it's going to get a little bit funkier. Let's look at the first 4 derivatives. So, of course, f is, f is e to the 2x. F prime is equal to 2e to the 2x. F double prime is 4e to the 2x. And f triple prime is 8e to the, is 8e to the 2x. So if I plug a 2 into each of those, I get e to the fourth. I get 2e to the fourth. I get 4e to the fourth. I get 8e to the fourth. Alright, so those are going to be my coefficients. So e to the fourth plus 2e to the fourth x minus 2 plus 4e to the fourth x minus 2 squared over 2. And divide that by 2. I'd just get a 2. And then my final term would be plus 8e to the fourth x minus 2 cubed over 3 factorial. If I divide by 3 factorial, that's like 3 times 2 times 1. So this would become a 4. And that would become a 3. So there's my third degree polynomial centered at 2. It looks like in the third part it wants me to find an error for 2.2. Okay, so let's see, how would we go about doing that? Here's what we would do. If we wanted an estimation, so let's look for an estimation for e to the 2 times 2.2 using our polynomial. Well, that would be e to the fourth plus the second term would be 2e to the fourth times, of course here I'm going to put 2.2 in each time. So it would be 0.2 plus 2e to the fourth times 0.2 squared plus da-da-da. Right, 4e to the fourth times 0.2 cubed over 3. So that's going to shoot you out a number, right? So let's talk about error. Well, the error of this third degree approximation of 2.2 will be less than or equal to the fifth derivative. Okay, fifth derivative will be 16 e to the 2x, okay, times x minus 2 to the fifth power over 5 factorial. Now we're going to test two numbers here. First of all, in for x, we would immediately put 2.2 here, right? So this would actually be 0.2 to the fifth power. And that won't change, right? What's going to change is what we put in here into the derivative. So really what I should have here is the fifth derivative of, or 16 times e to the 2. I'm going to call that my z value. Right? And in here for z, I'm going to test two numbers. I'm going to test the center, right? The center, which is 2. And then I'm going to test the point, which is 2.2. And I'm going to figure out which one gives me a maximum. I don't have the space or a calculator with me, so you're going to have to do that on your own. But one of those would maximize the error. Not sure which one. Okay, I want to quick roll through this one as well. Alright, so I took three derivatives here, plugged in one, got each of the following values. So a sub 0 is here, a sub 1, a sub 2, a sub 3, etc. Okay, now this is a really interesting problem in this way. So if it asks you to take the limit, in this case as x approaches 1 of the following, okay, I'm going to leave the denominator alone, and I'm going to approximate just this piece, the square root of x, to be the polynomial that's formed using this Taylor series. So I did the polynomial expansion using that Taylor series here in red. And so I get, you can see I've got that in red. I got everything else written in black. And what's cool is this one and this one, they go see you bye. And then each of our terms actually have an x minus 1 in them. So what I can do is I can reduce each of the terms. This becomes a 1/2 there. And then I cancel out and reduce. Now, if I were to plug in now and do a direct substitution, as x goes to 1 of this, I've got 1/2 minus what will end up being 0 over 8, right, plus 0 over 16. And down the line, I'm going to get the same thing all the way across. My limit here is 1/2. So this is just a different way to do limits, which is actually quite awesome. Okay, I'd like to take and do a quick integration problem here, and these are pretty filthy, and they're actually like scary looking, right? I'm gonna do number 4 here real quick, but what I'm gonna do is the Maclaurin expansion of sine x, which is 1 plus, let's go x, oh I'm sorry, oh, totally jacked that one up. That will be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And I don't know how far out I'm supposed to go. I guess I'll go one more term. Minus x to the 7th over 7 factorial. And I'm going to divide all that by x. And then I'm going to integrate it from -1 to 1 dx. Okay, so the advantage of Maclaurin and Taylor is I can put everything into polynomial form, which makes integrating so much easier. So each of these terms, this term here will become a 1 So the integral -1 to 1 of 1 minus, that would be x squared over 6. Right? That's what that would become. Then I'd have x to the 4th over, oh boy, 120. I'm not going to do this term. I already see it getting messy. And now I can integrate from here. So if I integrate this, I'll get x. I'll get minus x cubed over 18. And oh goodness, I'll get x to the 5th over, that's 500, I think, is that 600? 5 times 120. Yeah, that seems right. Okay, and I'm going to go from -1 to 1. So just evaluate here. Let's plug in let's go +1. So that'd be 1 minus 1/18 plus 1/600. Oh gosh. Minus, we'll plug in -1 here. That'd be -1 plus 1/18 minus 1 over 600. Okay, so it looks to me like whatever one of these is, it's just going to double that. Let's see, 1 minus -1 will be 2. -1/18. Let's see, so minus 2/18. And plus 2 over 600. Okay, I don't know what that is, and I don't really care right now, but you could do that math. I'm not going to right now. So that's how integration can be used using a Taylor or Maclaurin series. In this case, Maclaurin, which makes it much easier to integrate. So, all right, that's it. That's all for the 8th chapter on Taylor and Maclaurin.